So work, energy, and power. Two of these things are actually really the same thing. They have some of the kind of the same equation, and then one of them is a little bit different. So the first one I'll look at is work. We've had an equation for work before. Anybody remember what it is? How do you calculate the amount of work done? Force times displacement, right? Force times displacement, okay? And that's important because these are vectors, so they're actually in the same direction, right? So if I'm carrying, carrying a box across the room, my force is upwards on the box. So that's not that, but the direction is, to the right. So that's not actually work. You have to actually be, I have a box here. I'm going to apply a force this way, and I'm going to move it a certain distance. And I take that force times that distance, and that would be the amount of work. Force is usually in newtons, and displacement is in meters. So if I take force times displacement, I have Newton meters, and that's actually a what unit? Anybody know the unit for work? Joules, right? It's joules. Okay, joules. So that's the amount of energy that we have in, or the units we have for work or energy. Work and energy are really kind of the same thing. Okay. And we've had this before when we dealt with the simple machines, right? Everything was about the work, right? It was force times distance. That was your trade-off in simple machines. Okay. So we have a problem 3.8 on this page. 3.8. It says a student lifts a 50-pound ball 4 feet in 5 seconds. So it's a 50-pound ball, and we're going to lift it up 4 feet. And we're going to lift it up in a certain time, 5 seconds. Now, the equation we're just looking at right now is force times distance, displacement. So the time is completely irrelevant, okay? But before the lecture's over, we're going to talk about power, right? So that's when time becomes relevant. So in this particular problem we're doing right now, we don't have to worry about this. But later on, we're going to do a follow-up problem. We're going to refer back to this problem, and then we'll have to apply this. Okay. So if you're thinking, well, what's the time of doing it? It actually doesn't have anything to do with this particular problem, but it will a little bit later. So we want to figure out how much work is done, and we want to take the force, right, times the distance. Problem is, if we want this to be in joules, we have to do a little bit of dimensional analysis, right? We need some conversions because this can't be this is 50 pounds. It can't be 50 pounds. It has to be, the weight has to be in newtons, right? This can't be in feet. It has to be in meters. So there's some conversion factors there. It says 1 Newton is 0.225 pounds. So I can do 50 pounds. And then I can just do 0.225 pounds is 1 Newton. Okay, so I can do that. So 50 divided by 0.225 is 222 newtons. Okay, and then we have 4 feet. And the conversion says 1 meter is 3.28 feet. So feet would cancel, right? I can do 4 divided by 3.28, and I get 1.22 meters is how far it's going to get lifted. Okay, so the major part of this problem is, convert everything into the right units first, right? And now to figure out the amount of work to do, all we have to do is take force times displacement, right? Pretty easy. So 222 times 1.22, I get 271 joules of work. So there's your answer for 3.8. All right, any questions on that? That's kind of, we've done those problems before, so hopefully it wasn't, I am kind of going a little fast today, so. Okay, on that page on 94, you'll see gravitational potential energy, there's kinetic energy. We're going to talk about different kinds of energy. So gravitational potential energy is like energy of position. That's a height. So what happens is, like, if I take this calculator and I lift it up, I take something and I lift it up, then it's gaining gravitational potential energy. And if I let it go, what happens? It starts to fall, which is, now it's moving, right? It's energy of motion. So this is kinetic energy as it's going down, kinetic energy. Gravitational potential energy is energy of position, and then that can convert back and forth. So if I lift something up, I'm storing energy into it. I'm getting more and more gravitational potential energy. I let it go, and it's going faster and faster and faster, and it gains kinetic energy. So what I can do is a conversion, conservation of energy. If I lift something up this high, this has 100% gravitational potential energy. It can be a certain amount of joules. Let's say it's 100 joules. Well, when this falls down, it's going to be converted into kinetic energy. At the bottom here, the kinetic energy would be like 100 joules. Up here at the top, it's still 100 joules of stored energy. Okay. So this is going to get converted back and forth. It's conservation of energy. We talked about conservation of energy. And what we did back when we did simple machines is we did a percent efficiency, right? So we have energy output over energy input times 100%, right? Remember the efficiency? And the idea is you could never, you can't get more energy out than what you put in. In fact, you can't even get the same amount of energy out that you put in, right? You're always going to lose energy. And the important thing for that back in the day was, when simple machines was, energy was, work was force times displacement. So even though we always knew that you can't have a 100% efficient machine, we would still do it, right? Because it was all about the force. Yes, I'd have to push it a long ways, but I could lower the force down to something that I could actually do, right? It still didn't matter. I'm still going to lose energy over time, but at least this machine allows me to be able to do the work. I wouldn't even be able to do the work if I didn't have the machine. But the energy is still going to be, efficiency is going to be less than 100%. Okay. Literally all of that we've technically already lectured on a long time ago. But we're going to talk about it again. I thought it'd be good to just kind of review some of that. Okay, so the next thing we're going to introduce then, that's energy. So energy is or work, and that's force times displacement. Right? Energy or work, force times displacement. So now what I want to talk about today is power. Okay, power. Power is just power is pretty easy. Power is just how fast you can do the work, right? Okay, so I'm always trying to get students to do work. I'd love to be able to sometimes just have all my students do work and then do it quickly, right? I'd like to be able to move faster than we can sometimes. So power is just work. It's a rate of work, so it's work over time. That's the only thing we have to throw in to figure out power. It's just work over time. That's pretty funny, right? Power is work over time. Get it? Work over time? Okay. Or energy over time, right? Energy over time, it's the same thing, work and energy. Okay. So I could actually do energy or work is force times displacement. So I could do force times displacement over time. There's a whole bunch of little equations I could write for this. I could write in different ways. I could even do it like this. Does anybody know what displacement over time is? Especially my physics student. Displacement over time. Miles over hour. Miles per hour. Meters per second. What is that? Yeah, it's how fast you're going, right? Okay, now if we do a vector, it's velocity, right? That's, you know, some people use those interchangeably. So power is also force times velocity. The force times how fast it would be like moving along. Okay, so that's another equation for power. So the units for power, energy or work, we've already said is joules, right? And what's the units for time? Seconds. Yeah, it's always seconds. Now we can do minutes and hours stuff, but we always MKS them in physics. So it's going to be joules per second is going to be power. What is that? Joules per second. What is that? What are the units for power? I'll say it again. What are the units for power? Watts. Yeah, you're supposed to just say correct. I wasn't actually asking a question. But that was funny, right? What are the units for power? Joule per second, that's called a watt. Okay, power is in watts. Power is in watts. You got a 25 watt light bulb, that means it's that's how much power it's drawing, 25 watts. Okay, so 3.9, there's a question 3.9 says how much power was used in problem 3.8. So if you go back to 3.9, refers back to 3.8. Now how much energy did we use or work did we have in 3.8? What was our answer? 271 joules, right? So how do I figure out how many watts of power were used? I got to take the energy and then divide it by the time, right? It's energy over time. Work over time is your power. So 271 joules divided by was 5 seconds, right? So 271 divided by 5, I get 54.2 watts of power. Okay, so power is, there's different ways to write it. Power is, work over time or energy over time, F times D over time, or my personal favorite, force times the velocity. Okay, and then that kind of comes to what we're trying to do, because right now we're talking about energy unit and the energy unit, and we're talking about electricity, basically, right? Electrical energy. So electrical power is calculated by taking V times I. What's V? No, this is electrical power. You're talking about your electrical circuits in there. What's V? Voltage. And what's I? Amps, right? Current. It's current, but it's in amps, right? So volts times amps. That's how you figure out how much electrical power is like going through something. So if I have like, I have an electrical circuit and then I got this, light bulb in here. Okay. So, and there's a resistor and there's a battery and stuff, all kinds of things. You have the ability to be able to figure out the current in a system, I hope. Now, right? Remember V equals IR, right? So you can figure out the current in a system. You can also figure out how much voltage drop happens over different things, right? So now you put that together. If I figure out the voltage drop across this device right here, the voltage drop, and I also know what the current is going through it, right? I can multiply that current times the voltage drop through that thing and figure out how many watts of power this light bulb is pulling. Okay, so if you have a 25-watt light bulb, and you know the current going through, then you're going to know how much voltage drop is across that light bulb. Okay, this is a very simple equation. Power is volts times amps. Okay, and you're going to get questions like that on this next task that we're going to do. Okay, you're going to be able to figure out the power of something, or if I tell you what the power is and I tell you what the current going through it is, you'll be able to tell me right away what the voltage drop is. Okay, you can do it another way as opposed to the Kirchhoff's voltage laws. You can actually, tell me what it is. But this still is in watts, right? Volts times amps, okay, is in watts. Okay. By the way, we used to have a different measure. Instead of watts, we had a different measure of power. Back in the olden days, the source of power was the horse, right? So we used to talk about horsepower. I mean, it was how much power basically a horse could do, right? And literally, that's what it was. So there's a conversion factor in case you end up needing it. It's in your book, so you always have it. So 1 horsepower is, I actually wrote 746 watts. Normally, like in physics, I just round it to 750. It's easier to remember. 1 horsepower is about 750 watts. Okay. So in case we need to convert something to horsepower, that would be how you do it. Okay. So I want to stick on this just a little bit longer. So if the equation for electrical power, so like just regular mechanical power, is like force times velocity, right? So electrical power is current times voltage, right? Then I have to write it. So if this is electrical power, electrical power, what's the equation for electrical energy? If amps times volts, IV is power, what is electrical energy? Well, power equals energy over time, right? Power equals energy over time, right? And so energy, we're trying to figure out energy, right? Energy would equal power times time. That makes sense? So energy is power times time. So what's the equation for electrical energy? It'd be power times time. And what's power? Power is the volts times the amps, right? So I need to take that times time. Does that make sense? Power is energy over time. So energy is power times time. Here's your equation for electrical power. So your electrical energy needs to be volts times amps times time. Okay. So we always kind of discuss this question because I think it's interesting and you should probably understand it and know it. You get a bill for all the electricity and stuff in your house, right? Every month you get a bill. I don't know if you knew that or not. Your parents get it. They pay it. You probably should, pony up some cash or something for them so you can continue living in their house. So is the bill that they get, is it a electrical energy bill or is it an electric power bill? Is it an energy bill, or I mean, just by the physics terms of it, is it an energy bill or is it a power bill? Why? Okay, but time is actually already in power also, right? I mean, this just because you don't see time in here. Remember, what is power? Power is energy over time, right? So this power has its dealing with time also, right? And if you multiply this by the time, then you get the energy. But this, if you divide this one by the time, you divide this by time, see, you get power. right? Okay. But that's good thinking though, because time is part of that bill, right? It's how long you leave your lights on, right? That's always that making the meter spin, right? Do you know what the units are? Like if you have you ever looked at a bill? Like right in the bill, it tells you what the units are that you're buying. Anybody? No one's ever seen that? Really? You should ask to look at the bill when you get home today. Okay? You'll see that it's in kilowatt hours. It's a weird unit. Kilowatt hours. Have you heard of that? Haven't even heard of that, huh? Really? Okay. All right. Well, someday you're gonna have to join the world and you're gonna get a bill and you're gonna go, what is this? You know, kilowatt hours, you know, and that's what they're charging you. They're charging you a certain amount of money per kilowatt hour. I can't remember what it is. Someone should ask Siri real quick. I don't know, it's like maybe 10 cents, maybe 10 cents per kilowatt hour. Kilowatt hour, KWH is kind of how it probably would be listed on the bill, maybe. I don't know. No, I'm kind of curious. Someone asked, what's the going rate for a kilowatt hour? California is a lot more. Okay, so I should live in Iowa. Okay, so this is the unit that they're charging you. Kilowatt hours. What that unit is? That unit energy, or is that would that be an energy unit, or would that be a power? Why? This one, a kilowatt, is a unit for power, right? And this is a unit for time. So this is power times time. What's power times time? It's energy, right? Energy is power times time. This is kilowatts. That's a unit of power. It's not the actual unit we use. We use watts, and we use seconds here generally in a math problem. But they did kilowatts and they did hours, and they did that, by the way. How come? If they actually did this at watts and they did this in seconds, it wouldn't cost anymore. I mean, this price is still going to be the same, but on your bill, it would look huge. Yeah, it'd be a huge number, right? And they're just trying to save printing, right? So they're using dimensional analysis to make it so they don't have to print out a big number and people panic. So instead of watts and seconds, watt seconds, that'd be another unit, right? A watt second is a joule, right? This is kilowatts times hours. So this is like a, seems really small, okay? And but it's still it'd be an energy unit. It's power times time. It comes from Mid-American Energy, probably. So that's another clue, but okay. But it is technically an energy. How much energy you used, right? Okay. So like if you can figure stuff out. Like if you have I don't know, you have a 25-watt light bulb in your room and you left it on all day today, right? So you left it on. So 25 watts is how many kilowatts? So it'd be divided by 1,000, so it'd be 0.025 kilowatts. And then you left it on all day today. We'll say like 8 hours. Take it times 8, right? 0.025. You can see how much money you owe your parents. 0.025 times 8 is like 0.2 kilowatt hours. Assuming it's 10 cents times like 0.1, you owe your parents like 2/100 of a penny when you get home. So pay up, people. Now that's just a 25-watt light bulb. If you're gonna leave, like a stereo system on or a fan going or a heater or something like that, that's gonna take a lot more, and it's gonna add up, right? Okay.